Alright, so this is the honors lesson video for section 17.3. And so remember, if you want easy access to all my videos, just subscribe to my channel because I don't put them on my website anymore. So this section is also very long. If you hadn't noticed, that's a thing in chapter 17. So I'm going to try to go quickly so the video isn't too long. So first we're going to talk about heats of blank. So the first one is the heat of combustion is the heat of reaction for the complete burning of 1 mole of a substance. So if you remember, the definition for combustion is when a substance burns in the presence of oxygen. So a lot of times it's a hydrocarbon, but not all the time. Like here we just have carbon, here we just have hydrogen. Anything burning in the presence of oxygen is going through combustion. Alright, so next is fusion and solidification. So the heat absorbed by 1 mole of a substance melting from a solid to a liquid at constant temperature is the molar heat of fusion. So it's kind of hard to remember that one because you don't normally equate fusion with melting, but that's what we call it when we're talking about molar heat. The heat lost when 1 mole of a liquid changes to a solid at constant temperature is the molar heat of solidification. Now obviously, let's say we're talking about water here. The heat absorbed when the ice is melting into water versus the heat lost when that same amount of water is freezing, that should be the same number, but because one is absorbed and one is lost, the only difference is the sign. So delta H of fusion is the negative of delta H of solidification. So the number would be the same, the sign would be different. So another case where that happens is with vaporization and condensation. So the heat absorbed by 1 mole of a substance changing from a liquid to a vapor is the molar heat of vaporization. So we're boiling at that point. The heat released by 1 mole of a substance changing from a vapor to a liquid is molar heat of condensation. So again, since vaporization and condensation are two opposite processes, the delta H is the same, it's just the sign that's different. Alright, so let's look at a little chart real quick and see if we can read a graph. Alright, so delta H of fusion is blue, delta H of vaporization is purple. So it says, what's the delta H of vaporization for acetone? So I look at acetone, I look at my purple, delta H vaporization is a little bit under 30. So I put 29. I picked kilojoules per mole because it told me those were the units for my y-axis. Then it says, what is the delta H of condensation of water? So here's water. Now we don't have a delta H of condensation, we have fusion and vaporization to pick from. So what's the opposite of condensation? Vaporization. Okay, so that means I'm going to find my vaporization for water, which is just above 40, but I'm going to make it negative because it's condensation. So I picked to do about 41 for vaporization, so of course condensation would be negative 41 kilojoules per mole. Alright, next it says, what is the delta H of fusion of rubbing alcohol? So fusion's blue, so I go to rubbing alcohol, it's just right above 5, so I picked 6. So I put about 6 kilojoules per mole. And then the last one says, what is the delta H of solidification of diethyl ether? We don't have solidification. We have fusion and vaporization. So solidification is the opposite of fusion. So I find diethyl ether. It's right kind of in the middle of 5 and 10. So I put about 7 probably. But we're talking about solidification, not fusion. So I would put negative 7 kilojoules per mole. Okay, so you gotta be real careful with signs in thermochemistry. That's very, very, very important. Alright, so the last delta H we need to talk about is delta H of solutions. The heat change caused by the dissolution of 1 mole of a substance is the molar heat of solution. So in other words, the heat change caused when you dissolve 1 mole of a substance in a solution, so in water, for example, is molar heat of solution. It can either be positive or negative. So here we have sodium hydroxide dissolving into its ions, and it has a delta H of negative 445.1 kilojoules. So of course that one would be exothermic because the delta H is negative. So this is just the heating curve for water. Just make sure you understand what's happening. The most important thing I want to point out right now is the temperature change. So here we're at negative 10, so of course we have ice or solid water, and we can heat it. Eventually we hit 0. Once we hit 0, if we keep heating it, what's going to happen? Well, it's going to start melting. But notice the temperature does not change anymore. It stays at 0. I know that's hard for some of you to accept, but that's just really what happens. What is happening here is even though you're still adding heat energy, that energy is being used to help change it from a solid to a liquid instead of increasing its temperature. Remember, energy can do different things. It doesn't always have to stay in the same form. Alright, so it melts here at 0 degrees Celsius the entire time. Once it's all the way melted, the temperature can increase again. So now it's a liquid, So we heat it to 100. Then of course at 100 degrees Celsius, that water is going to start to boil. But notice it's going to remain at 100 degrees the entire time until all of the water boils. Okay, remember, during a phase change, temperature does not change. If you can somehow keep all the steam that you form, you can then further increase it while it's a gas. But while it's boiling, while it's melting, temperature stays the same. All right? So let's look at an example of a question. So it says, how much heat in kilojoules is absorbed when 24.8 grams of water liquid at 100 degrees Celsius and 101.3 kPa is converted to steam at 100 degrees Celsius? So the important thing to notice is there is no temperature change, so I cannot use Q equals MC delta T because there's no change in temperature. However, there is a phase change. We're going from liquid to steam, so what should that make you think of? Delta H of vaporization. So you should have a thermochemistry charts page. It looks like this. Your delta H of fusion and vaporization are right here on this middle chart. And so if you look for water, delta H of fusion 6.01 and vaporization is 40.7 kilojoules per mole, of course. So that's 40.7 kilojoules per mole. So I have to look. I'm starting with 24.8 grams of water. But then I'm given 40.7 kilojoules per mole. So of course my first thought should be, oh, I need to change this to moles. So when I add up water off the periodic table, I get 18 grams in 1 mole. That's just molar mass. And then I can use this as a conversion factor. 40.7 kilojoules equals 1 mole. Whenever you have double units like that, you can always make it a conversion factor. So once I multiplied and divided for that one, I got 56.08 kilojoules. Okay, so this is kind of similar to another lesson video where we did the stoichiometry, except you just don't have a reaction to use. You're just using your phase changes. All right, so let's look at another one together. So the next one, it says, how much heat is absorbed when 63.7 grams of water solid or ice at 0 degrees Celsius and 101.3 kPa is converted to liquid at 0 degrees Celsius? So again, no temperature change, but there is a phase change. Okay, if there was a temperature change, we use Q equals MC delta T. If there is a phase change, we use delta H of fusion or delta H of vaporization. I'll show you what to do if there's both in just a minute. Those are going to be some of y'all's least favorite ones. But I love them. I love doing heating curve problems. Alright, so what is solid to liquid? That should make you think of delta H of fusion. And so if you look at the charts page that I gave you, delta H of fusion for water is 6.01 kilojoules per mole. So I start with what I'm given, and that's 63.7 grams of water. And so I use molar mass of water again. So 1 mole of water is 18 grams of water. And then I can multiply by my delta H of fusion. And so once I multiply and divide for those, I got 21.27 kilojoules. Just like that. Alright, so let's see if you're really catching on. I'm going to let you try the next one. Alright, so let's erase this one. So, just pause the video real quick, try it on your own, and then we'll try it together. So it says, how many kilojoules of heat are absorbed when 0.46 grams of chloroethane, there's your formula, vaporizes at its boiling point? And here I just went ahead and told you what delta H of vaporization for chloroethane is. Now, if I had asked you about condensation, but gave you vaporization, you would need to make sure to know to change that sign. Okay, you gotta be careful of signs on here, but I asked you about vaporization and I gave you vaporization, so we don't need to change any signs. Alright, so the first step, of course, is I need to get to moles. So I take my chloroethane and I add up the molar mass. And when I added it up off the periodic table, I got about 64. So my grams cancel. And then I just multiply by my 26.4 kilojoules per 1 mole. And so once I multiplied and divided, I got 0.189 kilojoules as my answer. Alright, so hopefully you got that one right. Okay, so let's look at another one real fast. it says how much heat in kilojoules is released when 2.5 moles of sodium hydroxide is dissolved in water. Here's your molar heat of solution. So pause the video real quick, you try this one, and now we'll try it together. So I start with 2.5 moles of sodium hydroxide. Then the previous ones, my first step was to change to grams. I gave you grams to change to moles. But in this case, I already gave you moles, so we don't need to use molar mass. We just go directly to that molar heat of solution. So I do my negative 445.1 kilojoule per 1 mole for sodium hydroxide. And so in this case, all I need to do is multiply. And when I multiply, I got negative 1,112.75 kilojoules. Okay, so again, you got to be careful. If I give you moles, don't try to convert it to moles. I've already given you moles. Just use it and go to the next step. All right, so hopefully again you got these right. So let's move on. And see if you can get this one. All right, so pause the video, try it, and obviously we'll try it together right now. So how many moles of ammonium nitrate must be dissolved in water so that 88 kilojoules of heat is absorbed from the water? Okay, so we're dissolving, and then I gave you molar heat of solution is 25.7 kilojoules per mole. So this one, y'all, it's just a little bit backwards. That's the only thing. Okay, I'm going to start with 88 kilojoules, and we're trying to get to moles. So remember, golden rule says whatever's on top goes on bottom. So this time, I'm just going to put the kilojoules on bottom, and that equals 1 mole. So kilojoules cancel. Now notice it asked me for moles. If it asked me for grams, I would have to do another step where then I use molar mass to get to grams. Then it only asked me for moles this time. So once I divide for this one, I got 3.42 moles of ammonium nitrate. Just like that. Okay, so just know it can go either way. You can start with the grams or moles and go to heat. You can start with the heat and go to grams or moles too. The conversion factor works either way. All right? So let's move on and talk a little bit more about this heating curve. So sometimes a question might ask you about a physical change that involves a temperature change and a phase change. This is what I like to call a heating curve problem. We have to do these in multiple steps, and you have to work your way through the heating curve. So I did the color coding thing on the next couple of slides so you can see where everything is lining up with the heating curve. All right, so remember, here's the heating curve. When you have a temperature change, which is any of these red lines, you can use Q equals MC delta T. The thing you have to be careful of is on your thermochemistry charts page, those specific heats. Ice, liquid water, and steam all have their own specific heat. So that's why these are 3 different steps. The C's will be different. For ice, it's, I think, 2.1. Let me double check. Yep, 2.1. For liquid water, it's 4.184. And for steam, it's 1.7. All right, when you're at a phase change, there is no temperature change. That's what we just learned how to do on the previous slides. Delta H of fusion and vaporization are going to be different. Delta H of fusion for water is 6.01. Delta H of vaporization for water is 40.7. So you just got to be careful. All right, so let's look at how you do one of these. So it says calculate the amount of heat required to change 50 grams of water at 75 degrees Celsius to steam. So the first thing I would do is draw myself a really generic heating curve and figure out what we're doing so I can know how many steps. So we're starting at 75 degrees Celsius. Okay, so clearly here's 0, here's 100. So I just pretended like this is about 75. And we are converting it to steam at 100 degrees. So every time you make a turn on the heating curve, like see how here I have to turn this corner? That is a second step, or a separate step, because here there's 2. But you could have up to 1, 2, 3, 4, 5. 5 is the most steps you can have. All right, so whenever you are on a slanted line, you can use Q equals MC delta T. All right, so I'm going to do the blue line first. So Q equals MC delta T. So my mass is, of course, 50 grams. Here, I'm talking about liquid water. The specific heat for liquid water is 4.184 joules per grams degrees Celsius. And then next, I need my temperature change. Well, on this blue line, I'm starting at 75 degrees Celsius. I'm going to 100 degrees Celsius. So my temperature change, of course, would be 100 minus 75, which is 25 degrees Celsius. So my Celsius cancel, my grams cancel, And so when I solved this first step, I got 5,230 joules. Okay, so this is the number that goes with just the blue line. I have not done the red line yet. All right, so now I move on to the red line. Well, here we have a phase change, no temperature change. So I need to use my delta H of vaporization because we are boiling right here. Okay, so delta H of vaporization for water, we already know is 40.7 kilojoules per mole. All right, so I was given 50 grams of water. So my first step is to use molar mass. So 1 mole of water is 18 grams. And then I can multiply by that delta H of vaporization. Alright, so once I multiplied and divided there, I got, let me make sure I'm looking at the right one, 113.06 kilojoules. Once you have all your steps, you just add them together. But the problem is, for Q equals MC delta T, I'm going to get joules. For my phase change, the delta H's, I'm going to get kilojoules. So the easiest thing to do is just convert one. It doesn't matter which one, I'm just going to do joules. So remember, we know kilo, 1 kilojoule equals 1,000 joules, so I just divide by 1,000, or move that decimal 3 places, so I get 5.23 kilojoules. So then I just add them together. So I have 5.23 kilojoules plus 113.06 kilojoules. And so when I add those together, I got 118.3 kilojoules. All right, and then I rounded there a little bit, obviously, because you can see I don't have that last decimal place. All right, so real quick, I'm going to erase this and just show you the color-coded version so that you can see how it relates to my color-coded periodic table over here. So this part is the blue, this part is the red. Here I chose to do kilojoules to joules on here, and then my answer ended up being in joules, but we just got kilojoules a second ago, which we got, of course, the 118.3 by moving that decimal. So it doesn't matter what you give your answer in because it didn't specify what I needed. All right, so let's look at another one.
Hi, interruption.
Yes?
Fine.
This is my planning period.
Okay, thank you.
Try to make a video during my planning period. Oh well. Alright, so it says calculate the amount of heat needed to change 175 grams of ice at negative 20 degrees to water at 15. So if you feel like you might want to try this one, pause it and try it. I don't know if you'll be ready quite yet, but you're more than welcome to, but we'll go ahead and do it together. Alright, so we are at negative 20 degrees Celsius, so I just started down here, and then we are going to water at 15 degrees Celsius. So if you look, I have a blue line, a red line, and a green line, so I'm going to have 3 steps for this one. Alright, so on my blue line, I'm just going to tackle that one first. I have a temperature change. Remember, the 3 slanted lines, you can use Q equals MC delta T. So I'm down here in the blue, so I'm going to use Q equals MC delta T. So my mass is 175 grams. And then now we're at ice down here, or solid water. So we have to use the specific heat for ice. Okay, for water, it's 4.184. But for ice, on your charts page, it's 2.1. So we use 2.1 joules per grams degree Celsius. And then my temperature change. So you have to be really careful here with that temperature change. Because we're not doing 15 minus a negative 20. If you look on our blue line, we're going from negative 20 degrees Celsius, and we have to stop at 0. So that's where you have to be careful. Okay, you can't just assume we're going all the way to 15. It's not ice all the way at 15, it's water at that point. Okay, so 0 minus a negative 20 is, of course, a 20 degrees Celsius change. So Celsius cancels, grams cancel. And so once I multiplied for this one, let's see, where am I? Oh, I see it. 7,350 joules, which I'm going to go ahead and convert, so 1, 2, 3, to 7.35 kilojoules. I'm just going to go ahead and convert because I already know I'm going to need to. Alright, so now we got to tackle this red line. Remember, there's no temperature change here. This is when it's melting, so that should make you think delta H of fusion. So we have to start with our grams, so 175 grams. And then we use our molar mass, so 1 mole of H2O is 18 grams. And And then we use our delta H diffusion, which if you look on your charts page is 6.01 kilojoules per mole. So the reason I use 40.7 up here is because we would do vaporization. The reason we use 6.01 down here is because we are doing fusion. So once I multiplied and divided there, I got 58.43 kilojoules. All right, and then we have one more line to tackle, this green line. So again, we have a temperature change, so I can use Q equals MC delta T again. So my mass is the same, 175 grams, but now we're at liquid water. So my specific heat for liquid water is 4.184 joules per grams degrees Celsius. And then the last thing is we have to assess this temperature change. We're going to start here at 0 degrees Celsius, and now we're going to end at 15. So on the green area only, 15 minus 0 gives me a 15 degrees Celsius change. Okay, so the thing you have to be careful for on these is using the correct specific heat and making sure you're getting those temperature changes right. All right, so once I multiply for that one, I got 10,983 joules, which I of course changed to 10.98 kilojoules. And so then the last step, I'm not going to rewrite it again. Last step is just, add up all three of these. Ooh, that looks really weird. All right, I added up all three of those and I got 76.76 kilojoules. Okay, so it's all about just figuring out where you're starting on the heating curve, where you're going to. Now I'll give you a hint about the next one. If instead of heating, we're cooling, we're going to go the opposite way down the curve. Okay, and that's what the next one's going to look like. All right, so I think there's only one more of these, thank goodness, because I'm sure this video is getting very long. It feels very long. All right, so it says calculate the amount of heat released when 100 grams of steam at 130, so I kind of started here, is cooled to water at 60. So in other words, again, 1, 2, 3 steps. If you'd like to try this one, pause the video and try it, but if you would rather just watch, then just watch your way through this one. So because we're cooling it, it doesn't really matter what order you do the steps in, but I like to go in the order of start to finish. So I'm going to start with my green one first. So because we're on a slanted line, we can start with Q equals MC delta T. So I'm going to start with that. So of course my mass is, look, where is it? 100 grams. Now up here, we're talking about steam, so you have to use the specific heat for steam, which on your charts page is 1.7 joules per grams degrees Celsius. Now we gotta be careful of that temperature change. We're starting at 130 degrees Celsius, we are stopping at 100. Now remember, we're cooling it down, so we're not doing 130 minus 100, we're doing 100 minus 130. So my temperature change is negative 30 degrees Celsius. So you gotta be careful of that. That's what I'm telling you. These signs are very, very, very important in thermochemistry. So once I solved, I got negative 5,100 joules, which of course I went ahead and changed to kilojoules. Now moving that decimal 3 places or dividing by 1,000. All right, so here I'm at delta H of vaporization for when we're boiling, but here we're cooling it. So I need delta H of condensation. So remember, on your charts page, delta H of condensation is the negative of vaporization. All right, so I start with my 100 grams of water. And of course, as we've done many times, 1 mole of water is 18 grams. And then I'm going to do the negative delta H of vaporization because we're doing condensation, so it becomes negative 40.7 kilojoules per 1 mole. And so once I multiply that through, I got negative 226.11 kilojoules. And now I'm to my blue step. Okay, so again, we're at a slanted line, so I can use Q equals MC delta T again. So my Q equals MC delta T. My mass, of course, is the same, 100 grams. But here I'm talking about liquid water. Oh God, let's hope the coughing doesn't start again. I'm talking about liquid water, so my specific heat is going to be 4.184 joules per grams degrees Celsius because we're no longer talking about steam. Now let's figure out what this temperature change is. Well, we're going to start at 100. We're cooling it down to 60. So 60 minus 100 is a negative 40 degree temperature change. So grams and Celsius cancel, and so when I solved, I got negative 16,736 joules, which of course I then changed to negative 16.7 kilojoules. So last step is the same. I take all three of them and add them together, and so my total, that's easier than drawing all those weird arrows that I drew last time. My total is negative 247.91 kilojoules. So that would be my final answer. Okay, so the important thing to remember is when you're heating, all of your values will be positive. When you're cooling, all of your values will be negative. Because you got to think, if you're heating it, it's absorbing energy at every single step. If you're cooling it, it's releasing energy from every single step. Okay? So, hopefully the heating curve problem didn't kill you too much. Remember, the longest they can possibly be is 5 steps, because 1, 2, 3, 4, 5. You can't make it any longer than that. So, let's go ahead and finish up, because I know this video is getting super long. Hopefully the battery didn't die. Oh gosh. Alright, section assessment. Whew, we're there. How does the molar heat of fusion of a substance compare to the molar heat of solidification? Remember, they're opposites. So the delta H of fusion is the negative delta H of solidification. Alright, and then how does molar heat of vaporization compare to molar heat of condensation? Well, again, they're opposites. So your delta H vaporization equals the negative delta H of condensation. Remember, two opposite processes will involve the same delta H with a different sign. Alright, so let's look at the next one. So it says, identify each enthalpy change by name and classify each change as exothermic or endothermic. Alright, so here we're going from liquid to gas. So what would that be? Liquid to gas would be delta H vaporization, because we're going from liquid to gas. And then is it exo or endo? Well, remember, we talked about this in another lesson video. Think about how fast the particles are moving. In a solid, they are slow. In a liquid, they are medium. In a gas, they are fast. If we speed them up, they absorb energy, endothermic. If we slow them down, they release energy, exo. So we're going from medium to fast, they're absorbing energy. So this would be an endothermic process. Alright, here we have liquid to solid. So we would have delta H of solidification. And so we're going from liquid, which is medium, and we're slowing it down to solid. That means we're releasing energy, so that would be exothermic. Alright, here we have gas to liquid. That is delta H of condensation. We are going from fast gas to medium liquid. So we're slowing down, releasing energy. So it is exothermic. Alright, sometimes I like to give it to you like this instead. Like I may give it to you in like the form of a reaction or something like that, and I'll put the delta H in there. So if the delta H is a reactant, would that be considered endothermic or exothermic? Well, if it's a reactant, that means it needs that heat in order to happen. So that would be an endothermic process. If heat is listed as a product, that would be exothermic because it's released as the reaction occurs. Alright, so this is solid to aqueous, so this is delta H of solution. And since heat is listed as a reactant, it is endothermic. It needs that heat it needs to absorb that heat in order to go from solid to aqueous. Alright, and then last one is solid to liquid. So remember, melting is the weird one, it's delta H fusion. And we're going from slow solid to medium liquid, so we're speeding up. So they have to absorb that energy, and that would also be endothermic. Alright, so I think that's all for section 17.3. And so hopefully it wasn't that bad, and hopefully it wasn't too long.